Hello, I'm Dr. Art Friedman. Welcome to the 9th Annual Chidon Hamada Yerushalmi, the Jerusalem Science Contest. This year, our subject matter is going to be nuclear science, and we're going to be using the book Introduction to Nuclear Science by Dr. Jeff C. Bryan. Here's a copy of the book, and everybody should actually have a copy by the time you've actually viewed this lecture. Now, the format of this exam is that I will be giving you perhaps 12 or 13 lectures during the next, over the course of the next few months, weekly lectures approximately, and these lectures will generally be about 1 hour in length, although they may be as short as 45 minutes or perhaps as long as 1 hour and 15 minutes, but I'll try to keep it down to that length. And basically, I'll be giving you an exam that might be anywhere from 25 to 33 questions each week, the week following the lecture. So you'll have some time to review that material. So we're going to begin, actually, by my giving you a short introduction to, which is actually not in your book, even though the book is called Introduction to Nuclear Science. One of the things that I think that we need to be talking about is actually the historical development of nuclear science. So we've had nuclear energy around since the beginning of time. So if I really wanted to do this historically, I'd have to go back perhaps 13.5 or 14 billion years ago when the universe was created. But we're not going to go back that far. We're going to start actually in the year 1895, at which time probably the first experiments were actually being done that led to our fundamental understanding of the atom. And in order to understand nuclear science, we really have to understand the makeup of the atom. So we'll begin there. Basically, if we go back to the year 1895, we find a scientist by the name of Wilhelm Röntgen, who was experimenting with something called a Crookes tube. And the Crookes tube actually looks, I've got one right here so I can show you what this is. There were a number of tubes similar to this. He actually started out with something called a Lenard tube, which looks sort of similar to this. I don't know if you can see this very well, but basically it's an evacuated tube. There's a vacuum in here, and there are 2 electrodes. On one side we have on this side here, over here, we have the positive end. And on this side, I'm sorry, I've got it backwards. This is actually the negative end. This is the cathode. And on this side, we have the anode, although you can reverse it. But on this particular tube, that's how it's set up. So basically, what he was doing was using a Lenard tube, which looked kind of like this, except there was a very, very thin aluminum foil window at the end of the tube. And if you pass a sufficient voltage across these 2 ends of the tube, you'll actually get a beam, and in this case it's a visible beam. It'll actually cause the screen, you notice there's a white screen right here, you'll actually cause the screen to fluoresce, and you'll see a green line across the screen. And I'll show you that later on, not during this lecture, but during one of the demonstrations. So basically he was using that kind of a tube, and he had wrapped the end of the tube because he wanted to make sure that no extraneous light was getting through the tube. So he wrapped the end of the tube with some cardboard to protect the end of the tube, and also to prevent light from being given off. And in the process of doing this experiment, the lights in his laboratory were dim, and he noticed that there was a screen of material that was a barium platinocyanide. He had a screen that was painted with this material. This is a material that was known to fluoresce, to actually glow in the presence of ultraviolet light. So he had this screen, and he noticed that when he turned his device on, when he passed several thousand volts across these 2 electrodes, that the screen suddenly began to glow. So it had been known at that time that there were a lot of minerals and there were other kinds of materials that when they were exposed to light, to ultraviolet light, they would glow. And he thought, well, maybe there's some ultraviolet light that's leaking out of here. So he wrapped this thing really well. He changed from the Lenard tube with the thin aluminum window, he changed to another kind of tube, the Crookes tube, that we have here, and he used something where there would be less likelihood of any of the light actually penetrating, anything going right through the window. So the glass would actually hold this in, and he wrapped this very, very well. Wrapped it with cardboard and other kinds of black paper to prevent any extraneous light from getting out. And he had also moved the screen to the far end of the laboratory. And lo and behold, when he turned the device back on, everything was very, very dark in the room. But he noticed that that screen at the far end of the laboratory was actually still glowing. And when he turned the device off, it stopped glowing. So he realized that something very unusual was going on, and there must have been some kind of invisible form of energy that was coming out of this device. And he did a lot of experiments with this, and he ultimately found, for instance, that these invisible rays, which he referred to as X-rays, would actually pass through a lot of solid matter and would actually develop or form an image on a photographic plate if it was kept in the dark. So he did one experiment where he got Frau Röntgen, Anna Röntgen, his wife, to hold her hand in between the beam and the photographic plate, put it on top of the plate, and then when he developed the plate, what he saw was the very, very first X-ray that was taken of a human being, and it was his wife's hand. And when he showed it to his wife, she remarked, "I have seen my own death." So that was kind of an interesting observation. Today, this is very, very commonplace. This is how we take X-rays. But back then, it must have been pretty scary to actually see her skeleton, the bones in her hand. So this was the beginning, really, of, we might say, of the atomic age. The discovery that there was some kind of invisible beam, this X-radiation. This was in 1895. And a few years later, in 1901, Röntgen was actually awarded the very, very first Nobel Prize in Physics for his discovery of what were at that time called Röntgen rays. He was a pretty humble individual. He didn't like them people naming it after him, so he just referred to them as X-rays. The following year, though, after Röntgen's work in 1895 and 1896, there was a Frenchman by the name of Henri Becquerel. And Becquerel was doing, influenced pretty much by Röntgen's work. He was actually very, very interested in seeing whether or not he could repeat some of these experiments. And he was also interested in this whole idea of fluorescence. That is, that there were certain minerals or chemicals that you could expose to light. And if you expose them to light and then put them in the dark, they would continue to glow. So, for instance, what happened was that Becquerel's father actually had a very extensive mineral collection, and he was also a professor at one of the universities in France. I've forgotten which one now, and as was Becquerel. And he had taken some of the specimens from his father's collection, and he was doing some work with them. He also had a specimen of a chemical maintained in kind of a squarish box, and this chemical was potassium uranyl sulfate, a uranium salt, which at the time was known to be one of these kinds of materials that if you exposed it to ultraviolet light, it would give off a bright green glow. So he was working with this material, and he had actually taken some of the material and wrapped it up with dark paper so there wouldn't be any exposure to light, and he was getting ready to take this outside. He was going to, I guess, put it into the sun, remove the paper, put it into the sun, and then bring it back into the lab and see whether it was going to glow or not. And before he did that, apparently he had laid this on top of a photographic plate, and it had been actually sitting on top of the photographic plate for a period of time, and when he removed it from the plate, he noticed that the plate had actually become fogged. That is, it had been somehow developed as though light had struck the plate. So he wrapped this up very, very well again, and he repeated this a few times, and he realized that there was actually something. He left this in the dark for a very long period of time. He knew it wasn't coming. It wasn't visible light that was actually shining on the photographic plate that was causing it to develop. It must be something very much like the emanations that Roentgen had seen, these invisible rays, but they must also be different than Roentgen's rays, because Roentgen's rays required a lot of energy. You had to actually put a lot of electricity between two electrodes in order to produce those rays. And here was a substance that, after all, wasn't being energized at all. It was just being itself, basically. It was sitting there, and it was giving off this energy, and it was causing images to form on photographic plates. So for his investigations, the work that Becquerel did, he was also awarded the Nobel Prize, and that was in 1903. And he shared that with Pierre and Marie Curie, who took his work a step further and actually helped elucidate a lot of what we now know about radioactivity, at least the earlier work that was done. So in 1903, the three of them shared the Nobel Prize in Physics for their work. And then the following year, in 1896, after Becquerel had done his work I'm sorry, it was 1897. Becquerel's work was in 96. There was a gentleman by the name of J.J. Thomson, who was also working again with this device that I showed you here, the cathode ray tube, the Crookes tube. And what Thomson realized was that the particles, that this beam of whatever it was that was actually streaming from the cathode to the anode, that beam was actually composed of some kind of a particle which could actually be moved either by a magnetic field or by a perpendicular electrical field, so that if you stuck an electrical field, if the direction of transmission was horizontal and you stuck an electrical field above these plates, so that you had a negative end and a positive end, that in fact these particles would always move towards the positive end. The beam would actually be deflected towards the positive end, indicating that the beam itself must consist of electrically charged particles. And thus Thomson had actually discovered the presence of something that we now know as the electron, and that's what he called it, the electron. These were thought to be very small particles, a lot smaller than the other kinds of particles that you would get out of the atom, and in fact we know that to be the case today. So Thomson also, for his work, won a Nobel Prize in Physics, and that was in 1906. Now, sometime later, in the early part of the 1900s, Ernest Rutherford, along with two associates, Hans Geiger and a graduate student of his whose name was Ernest Marsden. Marsden and Geiger. Marsden, we don't really hear too much more about him, but Geiger actually went on ultimately to develop what we now today call the Geiger counter, a way of actually detecting radioactivity. But the three of these gentlemen conducted a very interesting experiment, or series of experiments, which I'm going to try to illustrate for you. And the idea was this. They were actually looking at something that Thomson had proposed earlier on, Thomson's idea of what an atom looked like. Thomson believed, and there was a lot of controversy about this, but Thomson believed that an atom, if you had an atom, basically at that time the only thing that was known about an atom was that it consisted of particles that were called protons and other particles that were called neutrons. Rutherford had actually discovered the proton from some experiments that he was doing, and as I said, the electron was already known. The neutron had not yet been discovered. The neutron was to come later on, but the proton and the electron were known. And basically, the model was that there's kind of a sea of electrons in the atom. There's electrons all over the place, and there's an equal number of positively charged particles called protons. And this was referred to as the plum pudding model, because basically the protons were just scattered throughout the pie here, if you want to look at it that way, much like you would find plums in a plum pudding. There was no particular order to these things. So, see if I don't know. You can actually see this when I'm drawing here. But I'm just trying to show you positive charges. It doesn't seem to be showing up very well. I'll try to write a little bit more heavily so we can see this, maybe see this a little bit better. And the rest of this are, the negative charges that are distributed in here. So basically, that was the generally accepted theory or explanation for the structure of the atom for many, many years, the plum pudding model. And then comes along Ernest Rutherford, and Rutherford does an experiment not trying to challenge or disprove Thomson's model, but actually trying to verify the model. Because Rutherford didn't believe that the model was necessarily wrong, but he felt we're going to do an experiment and show that in fact this is the correct model of the atom. And this is what they ingeniously devised. Marie Curie had worked in the latter part, and Pierre Curie had worked in the latter part of the 1800s and had isolated a quantity of radium bromide from uranium, and small amounts of that material were available to a number of researchers so that they could do some of this pioneering work. And basically what Rutherford did was he took some of this radium bromide and he put it into a little, we could call it a little cannon. Basically it's got a small hole in here. The radioactive sample sits down in here. The rest of this is lead lined, and basically the lead blocks most of the radiation, but through this one channel some of the radiation can actually escape, and it's going up through here. Now what he did was he fixed to this a screen that went kind of a large circular screen. It goes all the way around here. I'm kind of looking at this from above, basically looking in this way. And this screen is coated with a fluorescent material, zinc sulfide, which in the presence of alpha particles, which is what are actually being given off, the so-called, what was actually being produced by the radium as it disintegrated were these alpha particles. And the alpha particles would travel a certain distance, and if they went beyond a certain distance, they would actually probably wind up being absorbed by something, or they would hit something, and that would be the end of the alpha particles. But it was found that in this particular setup that the alpha particles could travel to the back of the screen. It's obvious it really wasn't as large as I'm making it. It was a much smaller device. But basically, this is a kind of a diagram of what they were using. So in the middle here, what they did was they put a thin gold foil, a thin piece of gold that actually was perpendicular to the beam. And the idea was this: if in fact the plum pudding model is correct, what you would expect is that there's going to be a lot of empty space in there, and some of these particles, which are known to be relatively small, at that time, as I said, the neutron wasn't known, but they had a rough idea of the size of this particle, and they also had a rough idea of the size of the atoms as well. And then they knew that the atom, the atom had a bunch of these protons in it, and they knew that the alpha particle had two positive charges, so there were at least these two protons. The alpha particle had to be larger than any individual proton that was in the gold. So if a proton was actually struck, what they expected would happen is it would get knocked out of the way, just like what happens in a collision between a large vehicle and a vehicle half its size. The smaller vehicle is going to get pushed out of the way pretty much, but there's going to be a deflection of the larger vehicle. So most of these particles, one would expect, are going to pass through and hit the screen, and they're going to cause the screen to glow. There's going to be a visible point of light where the particle actually hits the screen. And I've seen this. It's really quite remarkable to actually view this. And they would expect probably there would be very little deflection if it passed right through, but if it actually hit a proton, then you'd expect to see something like that. There'd be some kind of deflection of the beam. And they did in fact see this, but they saw some larger deflections as well. And most remarkably, they also saw, which they couldn't explain at first, they saw some things that indicated that an alpha particle was striking the screen and bouncing off of the screen, coming back this way. And in some rare cases, the alpha particle would actually come right back. It would be directed right back in the same direction that it propagated. So it would come back, it would come all the way back here. So this was most amazing. And Rutherford himself described this. He said it was almost as if you had taken a 15-inch mortar shell and you had fired it at a piece of tissue paper. And it hit the tissue paper and came and bounced back and hit you. He said that was how incredulous they found this to be. But when he thought about it further, he realized that perhaps this was an indication that Thomson's plum pudding model was incorrect. In fact, and we know this today, that what he was seeing was the fact that rather than having this large particle, which actually consists of 2 protons, and as I said, they didn't know that there were 2 neutrons in there, but it's essentially the size. The neutrons and protons are about the same mass. So this is something about the size of 4 protons, and the gold atom has 79 protons in it, and even more, over 100, I think, neutrons that are in it. So the gold atom is perhaps something on the order of, I don't know, maybe 50 times larger than the alpha particle itself. So now it's kind of like you've got a tricycle hitting a car, or a car hitting a tricycle hitting a car. You're not going to expect the tricycle to push the car out of the way. Rather, it's going to probably bounce off of the car. It's not going to do anything to the car. And so the only way they could actually explain this was, in fact, if all these protons weren't scattered willy-nilly all over the atom, but they were actually located in one point in the atom, and they assume this is at the core of the atom, at the center part of the atom, and this is called the nucleus. So in the nucleus of the atom. Now I'm going to erase the rest of this stuff because it's no longer my diagram of the experiment, but now this is what we would call, this is similar to what is today referred to as the Bohr model of the atom. And it's not the generally accepted model of the atom that we use. It's used in teaching chemistry because it's easier to visualize this when we first start teaching it. But actually, the quantum model, which we may discuss a little bit later on, is the generally accepted view of the atom. But in this particular view, what we have is still the idea that at the core, at the nucleus, we have the protons, and we also have the neutrons, not yet discovered. And then around, in shells or orbitals around this central part of the atom are arranged electrons. Now we're not going to be too concerned about these orbital electrons. It has very little to do. It has a lot to do when you're learning chemistry. It's the most fundamental part of chemistry because this is what actually determines chemical bonding. But for nuclear reactions, we're really going to be looking at the nucleus. And when we see an electron, occasionally there's going to be some involvement with electrons that actually are coming from the shells, but usually the electrons are emanating from the nucleus. What did he just say? They're emanating from the nucleus? How can that possibly be? There are no electrons in the nucleus. Well, that's true, but nevertheless we're going to see in a short while that in fact electrons do emanate from the nucleus, and they're referred to as beta particles. And I'll explain how that actually happens momentarily. So anyway, this is the model that we had up until that point in time. Okay, so now we've got we talked about Rutherford's work. In 1935, James Chadwick was doing some research and discovered another particle inside the atom. Chadwick was actually a student of Rutherford's. And actually, I think it was a few years before that. I think it was in '32 that Chadwick made his actual discovery. He was awarded the Nobel Prize in 1935 for the discovery of the neutron. That completes at least the the fundamental particles, not the particles that we know of today that are even smaller than that, but the particles that were known, at least that gave us the basic building blocks of the atom up until that time. And during the same year that Chadwick won the Nobel Prize in physics in 1935, Irene Curie, Joliot-Curie, and Frederic Joliot-Curie, her husband, Frederic Joliot made their names hyphenated after he was married. I mean, the Curies were such a famous family. Irene was the daughter of Marie Curie and her husband Pierre, and they had already won the Nobel Prize. And it turns out that the daughter, this one particular daughter, also, and her husband also wind up winning the Nobel Prize for discovering probably the first transmutation reaction, which was they actually were bombarding nuclei of one element, which was aluminum, and they were bombarding it with alpha particles, and they actually wound up producing a new element, which was phosphorus, and they were also producing neutrons in the process of doing that. So they won the Nobel Prize. The Joliot-Curies won the Nobel Prize in chemistry that year. Okay, so that basically gives us a little bit of an introduction, and now I'd actually like to begin the book. And the book starts with a statement that radiation is scary. I think radiation is more scary if you don't understand anything about it. But what is radiation? When we talk about radiation, we're talking about, at least in most cases here, we're referring to what we would call electromagnetic radiation. Now, technically speaking, particulate kinds of radioactivity, that is alpha particles and beta particles, or certainly alpha particles anyway, are not in the sense that when we normally talk about radiation, they're not probably what we would consider to be radiation in the classical sense. Radiation, when we talk about it, we're usually referring to electromagnetic radiation. When we talk about radioactivity, we tend to be referring to emanations that are coming from atoms, and they are the kinds of things that we can pick up in an ionization chamber. So this is ionizing radiation. An ionization chamber might be something like a Geiger tube, where we will actually produce an electrical signal when these particles, or in some cases rays, such as gamma radiation, when they actually enter the detection tube, and these signals are amplified, and they give us an electrical deflection on a meter, or we can actually hear a clicking sound in a set of headphones. I'll be showing you a Geiger counter later on as well, and you'll have an opportunity to see how those work as well. But basically, the ionizing radiation, when we talk about it, we're talking about electromagnetic radiation, which actually has to do with waves. Now, your book says something, and I want to correct it because it's actually in the second paragraph. And in this particular point, at this particular point, Dr. Bryan says, and I'll quote, he says, "Much of this chapter is devoted to definitions. In a sense, this chapter is a foreign language tutorial where you'll learn to speak some nuclear science." Now, I agree with all that. And then he begins to start with the topic of radiation. And he says radiation is energy that moves. And then he makes a statement that's very puzzling to me because I think he should know better. He says, more scientifically, it is energy propagated through a medium. Well, some kinds of waves are propagated through a medium, but the kinds of waves that we're talking about, electromagnetic radiation, are unique in the fact that they are not propagated. They may propagate through a medium, but it is not necessary for a medium to be present in order for them to propagate, in order for them to move. What do we mean by a medium? I mean something that is actually material. So we could say that if something's moving through the air, it's got matter in it, that is a medium. Water is a medium. Sound, which is another kind of wave, is propagated, has to be propagated through these kind of media, either a solid, a liquid, or a gas, because it requires that we compress we get areas of compression and rarefaction where the molecules or atoms move closer together and then they move further apart, and that creates a wave. Now we need that for things like sound, but for things like light or any form of electromagnetic radiation, we can go through the emptiness of space, of deep space, where there's really no material at all. There is no medium. And so, in fact, Dr. Bryan is wrong when he says that it's energy propagated through a medium. It's energy that's in motion. I will agree with that. Like he says in the previous sentence, radiation is energy that moves, but it does not have to be propagated through a medium. So I just wanted to correct that from the outset. This is a pretty well written book, so that was just one thing that caught my attention, and I wanted to clear it up. Anyway, so he goes on to tell you about the fact that this energy is actually can be thought of as being propagated in little packages. So let me just show you electromagnetic radiation. It moves. Something is vibrating. You could take a rope and vibrate it, move it up and down, and it produces a pattern sort of like that on the rope. And you can have the same thing electronically. You can have electrons that are vibrating, and when they do that, they're moving, they're also going to be producing waves. We call this a sine wave. And this regular pattern that we see in the waves, we can look at that, we can measure that in a couple of ways. We can measure, so if this is like this is the energy here, and this would be time. We're propagating through time here, and we could actually count the number of waves that we get in a particular period of time. Now, what constitutes a wave? Well, it's we could start, if we start here and we go to here, that's one wave. In other words, we started here, we went up, we came back down, and then we came back to our starting point. So that's one wave. And here's a second wave, and we could put a third wave in. Let's say, do I have enough to do that? Yeah, so we've got a third wave now. We've got one wave, this is the second wave, and this is the third wave. So if the period of time from here to here was 1 second, if we went from here to here, that was 1 second, then we would say that this wave had a frequency of 3 per second. We write that as 3 second minus 1. You could use SEC if you want to, per second. So 3 second minus 1. That unit, second minus 1, is 1 over second, is called the hertz. H-E-R-T-Z, and it's abbreviated Hz. So we call that the frequency. And frequency is abbreviated either using the Greek letter nu, or sometimes F. I'm not sure which one your book uses. Your book actually does use nu. Looks a little bit like a V, but that is the Greek letter nu. And it's found that you can actually get the energy of the wave if you know the frequency. There's also another thing that I want to talk about, two other things that we should know about waves. One of them is the amplitude. So the amplitude of the wave is actually, if we measure from here to here, that's giving us the height of the wave. You probably, I guess, measure it maybe from here, from the half height here. But that gives us the amplitude of the wave. And if you're talking about sound, for instance, that determines how loud or soft sound happens to be. The other thing that's more important is actually the wavelength. At least for what we're going to be dealing with, the wavelength, which is actually the distance from here to here. That's the length of one wave. So if we look at it this way, the length of the wave, and we use wavelength is abbreviated using the Greek letter lambda. So this is a lambda, L-A-M-B-D-A, and that stands for wavelength.